Corrosion can be a serious problem in any business that works with metal, including the shipping industry. The hostile sea climate, which contains high quantities of salt and moisture, makes ships prone to corrosion. If left neglected, it can undermine the ship's structure, posing safety risks and necessitating costly repairs. Corrosion is a process that occurs when metals move to their lowest energy state, resulting in a rapid response between the environment and the metal, reducing its quality and life. Corrosion is derived from the Latin word corrodere, which means gnaw to pieces. In case of the marine or shipping sector, mild steel is the most preferred metal for constructing ships due to its low cost, mechanical strength, and ease of fabrication. However, its main issue is that it corrodes quite easily as it comes in contact with the salty water of the sea. Secondly, if it is not properly protected, it loses its strength quite fast, which could lead to structural failure. While a way to prevent this is to repair the coating while the vessel is offshore, it can cost up to 100 times the cost of the first coating, and according to NACE International, the total cost of corrosion in the marine sector across the world is somewhere between $50 to $80 billion annually. However, if shipowners start with adequate planning and are careful with the first coating, their ships will give the best performance and maintain cost efficiency. If the reason for the deterioration is poor preparation of the surface, then the solution is to remove the paint and do it again. Protection against atmospheric corrosion is important during the construction of a ship, both on the building berth and in the shops. Serious rusting may occur where the relative humidity is above about 70%. The atmosphere in many shipyards is unfortunately sufficiently humid to permit atmospheric corrosion throughout most of the year. However, even in humid atmospheres, the rate of rusting is determined mainly by the pollution of the air through smoke and/or sea salts. When a ship is in service, the bottom area is completely immersed and the waterline or boot topping region may be intermittently immersed in sea water. Under normal operating conditions, a great deal of care is required to prevent excessive corrosion of these portions of the hull. A steel hull in this environment can provide ideal conditions for the formation of electrochemical corrosion cells. Any metal, intending to revert to its original mineral state, releases energy. At ordinary temperatures in aqueous solutions, the transformation of a metal atom into a mineral molecule occurs by the metal passing into solution. During this process, the atom loses one or more electrons and becomes an ion, with the production of an electric current. This reaction may only occur if an electron acceptor is present in the aqueous solution. Thus, any corrosion reaction is always accompanied by a flow of electricity from one metallic area to another through a solution in which the conduction of an electric current occurs by the passage of ions. Such a solution is referred to as an electrolyte solution, and because of its high salt content, seawater is a good electrolyte solution. A simple corrosion cell is formed by two different metals in an electrolyte solution. A galvanic cell, as illustrated in figure, it is not essential to have two different metals, as we shall see later. As illustrated, a pure iron plate and a similar pure copper plate are immersed in a sodium chloride solution that is in contact with oxygen at the surface. Without any connection, the corrosion reaction on each plate would be small. Once the two plates are connected externally to form an electrical path, then the corrosion rate of the iron will increase considerably and the corrosion on the copper will cease. The iron electrode, by means of which the electrons leave the cell and by way of which the conventional current enters the cell, is the anode. This is the electrode at which the oxidation or corrosion normally takes place. The copper electrode, by means of which the electrons enter the cell and by way of which the conventional current leaves the cell, is the cathode, at which no corrosion occurs. A passage of current through the electrolyte solution is by means of a flow of negative ions to the anode and a flow of positive ions to the cathode. Electrochemical corrosion in aqueous solutions will result from any anodic and cathodic areas coupled in the solution, whether they are metals of different potential in the environment or they possess different potentials as the result of physical differences on the metal surface. The latter is typified by steel plate carrying broken mill scale in seawater or corrosion currents flowing between areas of well-painted plate and areas of defective paintwork. In atmospheric corrosion and corrosion involving immersion, both oxygen and an electrolyte play an important part. Plates freely exposed to the atmosphere will receive plenty of oxygen but little moisture, and the moisture present therefore becomes the controlling factor. Under conditions of total immersion, it is the presence of oxygen that becomes the controlling factor. Although it is true to say that all corrosion is basically galvanic, the term galvanic corrosion is usually applied when two different metals form a corrosion cell. Many ship corrosion problems are associated with the coupling of metallic parts of different potential, which consequently form corrosion cells under service conditions. The corrosion rates of metals and alloys in seawater have been extensively investigated, and as a result galvanic series of metals and alloys in seawater have been obtained. A typical galvanic series in seawater is shown in table. The positions of the metals in the table apply only in a seawater environment, and where metals are grouped together they have no strong tendency to form couples with each other. Some metals appear twice because they are capable of having both a passive and an active state. A metal is said to be passive when the surface is exposed to an electrolyte solution and a reaction is expected, but the metal shows no sign of corrosion. It is generally agreed that passivation results from the formation of a current barrier on the metal surface, usually in the form of an oxide film. This thin protective film forms, and a change in the overall potential of the metal occurs when a critical current density is exceeded at the anodes of the local corrosion cells on the metal surface. Among the more common bimetallic corrosion cell problems in ship hulls are those formed by the mild steel hull with a bronze or nickel alloy propeller. Also, above the waterline problems exist with the attachment of bronze and aluminum alloy fittings. Where aluminum superstructures are introduced, the attachment to the steel hull and the fitting of steel equipment to the superstructure require special attention. This latter problem is overcome by insulating the two metals and preventing the ingress of water, as illustrated in figure. A further development is the use of explosion-bonded aluminum/steel transition joints, also illustrated. These joints are free of any crevices, the exposed aluminum to steel interface being readily protected by paint. Corrosion and subsequent failure associated with varying forms of applied stress is not uncommon in marine structures. Internal stresses produced by non-uniform cold working are often more dangerous than applied stresses. For example, localized corrosion is often evident at cold flanged brackets. Erosion. Erosion is essentially a mechanical action, but it is associated with electrochemical corrosion in producing two forms of metal deterioration. Firstly, in what is known as impingement attack, the action is mainly electrochemical, but it is initiated by erosion. Air bubbles entrained in the flow of water and striking a metal surface may erode away any protective film that may be present locally. The eroded surface becomes anodic to the surrounding surface and corrosion occurs. This type of attack can occur in most places where there is water flow, but particularly where features give rise to turbulent flow. Sea water discharges from the hull are a particular case, the effects being worse if warm water is discharged. Cavitation damage is also associated with a rapidly flowing liquid environment. At certain regions in the flow, often associated with a velocity increase resulting from a contraction of the flow stream, the local pressures drop below that of the absolute. Vapor pressure. Vapor cavities, areas of partial vacuum, are formed locally, but when the pressure increases clear of this region, the vapor cavities collapse or implode. This collapse occurs with the release of considerable energy, and if it occurs adjacent to a metal surface, damage results. The damage shows itself as pitting, which is thought to be predominantly due to the effects of the mechanical damage. However, it is also considered that electrochemical action may play some part in the damage after the initial erosion. Plate and section scantlings specified for ships in the rules of classification societies include corrosion additions to the thickness, generally based on a 25-year service life. The corrosion allowance is based on the concept that corrosion occurs on the exposed surface of the material at a constant rate, no matter how much material lies behind it. That is, if a plate is 8 or 80 millimeters thick, corrosion will take place at the same rate, not at a faster rate in the thicker plate. Some ship owners may specify thicker material than is required by the Classification Society, where there are plans for long-term ownership. The control of corrosion may be broadly considered in two forms: cathodic protection and the application of protective coatings. Only where metals are immersed in an electrolyte can the possible onset of corrosion be prevented by cathodic protection. The fundamental principle of cathodic protection is that the anodic corrosion reactions are suppressed by the application of an opposing current. This superimposed direct electric current enters the metal at every point, lowering the potential of the anode metal of the local corrosion cells so that they become cathodes. There are two main types of cathodic protection installation: sacrificial anode systems and impressed current systems. Sacrificial anodes are metals or alloys attached to the hull that have a more anodic, less noble, potential than steel when immersed in sea water. These anodes supply the cathodic protection current, but will be consumed in doing so and therefore require replacement for the protection to be maintained. This system has been used for many years, the fitting of zinc plates in way of bronze propellers and other immersed fittings being common practice. Initially, results with zinc anodes were not always very effective owing to the use of unsuitable zinc alloys. Modern anodes are based on alloys of zinc, aluminum, or magnesium, which have undergone many tests to examine their suitability. High-purity zinc anodes are also used. The cost, with various other practical considerations, may decide which type is to be fitted. Sacrificial anodes may be fitted within the hull and are often fitted in ballast tanks. However, magnesium anodes are not used in the cargo ballast tanks of oil carriers owing to the spark hazard. Should any part of the anode fall and strike the tank structure when gaseous conditions exist, an explosion could result. Aluminum anode systems may be employed in tankers provided they are only fitted in locations where the potential energy is less than 28 kgm. Impressed current systems are applicable to the protection of the immersed external hull only. The principle of the systems is that a voltage difference is maintained between the hull and fitted anodes, which will protect the hull against corrosion, but not overprotect it, thus wasting current. For normal operating conditions, the potential difference is maintained by means of an externally mounted silver/silver chloride reference cell detecting the voltage difference between itself and the hull. An amplifier controller is used to amplify the microrange reference cell current, and it compares this with the preset protective potential value that is to be maintained. Using the amplified DC signal from the controller, a saturable reactor controls a larger current from the ship's electrical system that is supplied to the hull anodes. An AC current from the electrical system would be rectified before distribution to the anodes. Figure shows such a system. Originally consumable anodes were employed, but in recent systems non-consumable relatively noble metals are used. These include lead-silver and platinum-palladium alloys. And platinized titanium anodes are also used. A similar impressed current system employs a consumable anode in the form of an aluminum wire up to 45 meters long that is trailed behind the ship whilst at sea. No protection is provided in port. Although the initial cost is high, these systems are claimed to be more flexible, to have a longer life, to reduce significantly hull maintenance, and to weigh less than the sacrificial anode systems. Care is required in their use in port alongside ships or other unprotected steel structures. Paints intended to protect against corrosion consist of pigment dispersed in a liquid referred to as the vehicle. When spread out thinly, the vehicle changes in time to an adherent dry film. The drying may take place through one of the following processes. 1. When the vehicle consists of solid resinous material dissolved in a volatile solvent, the latter evaporates after application of the paint, leaving a dry film. 2. A liquid like linseed oil as a constituent of the vehicle may produce a dry paint film by reacting chemically with the surrounding air. 3. A chemical reaction may occur between the constituents of the vehicle after application to produce a dry paint film. The reactive ingredients may be separated in 2 containers, 2 pack paints, and mixed before application. Alternatively, Ingredients that only react at higher temperatures may be selected, or the reactants may be diluted with a solvent so that the reaction occurs only slowly in the can. Thanks for watching. Please keep subscribed and share. See you in next video.